Thank you, Frankie, for that kind introduction. What I'm here to talk to you about, as Frankie said, is the role of solution processing in the future of OLED television. And this is one of the 55-inch TVs that Frankie mentioned that was shown at CES last year and at SID earlier this year. This is not one of our demonstrators, but it is one of the 55-inch ones. So what I'd like to talk to you about today is, first of all, why work on solution processing. OLEDs are made commercially already by evaporation. So I would like to talk about why we want to focus on solution processing for the future. Talk about the design principles that we used in designing our process, and then show you a cartoon of the process. Talk about printed device performance, combination of materials and process in a printed device. And then I'd like to talk about the scale-up path to large area manufacturing. What are the barriers, and then what are the things we are doing to work on scaling up the technology? So what I hope to show you today is shown here in summary. First of all, that solution processing is a key component to competitive large area OLED TVs. Our proprietary materials and then the process that we developed to work in tandem with those materials can deliver lifetime and color performance that's in line with the anticipated first OLED TVs. And then that we are addressing the challenges of rapid, so low tack time, large area patterning. So we certainly believe, and I think it's becoming commonly accepted, that the future of OLED requires a new manufacturing technology. The method by which the OLEDs are made today that you have in your cell phones they're made by evaporation, which is through a fine metal mask, and it has associated with it very high costs. The material waste is very high because you're depositing all over the chamber as well as on the substrate. The mother glass size is limited because of the issues with scaling up evaporators, although everybody is working on it, so some of those challenges are being addressed. Evaporators are more capital intensive, they're very expensive, and then shadow masks are costly and fragile, and they need to be replaced quite frequently. So our assessment looking at this some years ago was that solution printing was a good answer to these problems because we could have very good material utilization. Printing can be scaled to any size mother glass. Printers are much less expensive than evaporators, so your capital costs are much lower. And then there's no fine metal shadow mask. So if solution OLED's so great, how come everybody's not already using it is an obvious question. So there have been, of course, challenges in getting it to work. I think the biggest challenge has been developing the materials, the high-performance, soluble, solution-processable materials. So DuPont, as a chemical company, decided to take that approach of developing new materials for solution processing. And then in parallel, we developed the lowest cost process we could think of to combine those materials into the OLED stack. And there's a lot of issues we had to address along the way. How to coat the HIL, which is coated as a blanket layer, very quickly and at very thin target thicknesses. How to keep the printed inks just where we want them, and how to keep successive layers from mixing with each other. And then how to clean the substrates after we were done printing all over them so that we could make a good hermetic seal for the OLED materials. And then a big one, of course, is how to keep atmospheric conditions during printing from degrading the materials. So we developed a set of materials that can be printed in air. So everything you'll see in all the data is materials that are processed in air. So we decided to avoid having to put things under nitrogen because that was going to be too expensive. So the first material that was developed for solution processing by us was our DuPont HIL. And that's a water-based dispersion, which has a wide range of coating formulations possible. It must be solution processed. It can be, but having said that, it can be slot die coated or spin coated or printed, inkjet printed or nozzle printed. It's compatible with both evaporated and solution process top layers. We've shown that with a wide variety of materials. And it has a very high and stable work function, and it's very highly transparent, up to 100 nanometers thick. It's greater than 90% transparent in the visible. So this is a summary slide that shows you some printed lifetime data from a standard set of our materials with 100% on, so not video rate, but 100%. And these are printed bottom emission test coupons with no outcoupling enhancement. They are made in what we call a common architecture. So that means that we constrain the device architecture to require the same thickness of HIL and HTL and ETL for the three colors. That cuts down on the degrees of freedom for the device scientists, but it makes fewer patterned layers, which is a more cost-effective approach. So we obviously make some sacrifices there. We optimize the layer thickness for the weakest color, and so you will see, for example, in red, you don't see quite the same efficiency as you would see if we'd optimized the stack for red. But the weakest color is still always blue, and so the stack is optimized for blue, and then red and green have longer lifetimes. So the lifetimes with, and these I should mention are printed using our standard process by which we make displays with the materials printed in standard atmosphere. So the blue lifetime's greater than 40,000 hours, sorry, greater than 30,000 hours, the red greater than 40,000, and then green is unnecessarily long. And the efficiencies are shown here. Because we are a materials company, we're always working on new materials. So these are the next generation that are coming up. These are all solution process test results, but they're not printed. They're spin coated. So just want to make that distinction. So the red is more efficient than the one you saw in the previous chart. The green is much more efficient. And then this blue has a higher efficiency than the previous one was like 5.3. And then this is a deeper blue, 0.09 CIEY, which is a very promising material for displays as well. So these lifetimes, again, are bottom emission, no outcoupling, and no burn-in for these T95s. So I wanted to take a minute now and turn to the process and first talk about the principles that we applied when we started to work on this. We decided to solution process as many layers in the stack as we could. In our case right now, that's HIL, HTL or primer, and EML. We also wanted to pattern the minimum number of layers, so the common architecture I mentioned. And then when we do have to pattern, as in the EML, we want to employ a very robust tool. So we worked on a tool called a nozzle printer, which I'll talk more about in a moment. Wherever possible, we decided to not invent new equipment, but use standard FPD equipment. So slot coaters, for example, are available up to very large generation glass size. And then when we did have to have specialized equipment, we partnered with a very highly recognized FPD equipment maker, DuPont Screen, or Screen as they're known, for nozzle printing. So this chart shows you sort of a cartoon view of how we make our OLEDs. This is the back plane. And this represents the active area here in the cathode contacts. So we slot coat the HIL and primer or HTL layers. And then we come in and modify that surface to form wetting and non-wetting areas that then serve to contain the ink that we're printing with multi-nozzle nozzle printing. So now we come into, now it goes into an evaporator with a very coarse shadow mask that covers the entire active area. And we evaporate the ETL, the EIL, and the metal cathode over the active area. Now we use that cathode as a physical mask, still under vacuum. We haven't come out of vacuum. And we use a plasma etch process to remove all the organics that are everywhere else on the substrate. So now we've exposed the cathode contact, as you can see. And we've protected the OLED in the active area from the plasma. So now we just put down an aluminum capping layer, and you've made contact. And then we go through and encapsulate. We use a epoxy, glass bead-filled epoxy with a screen-printed getter on plain glass, which is cheaper than using cavity glass. But that's just something that we developed to cut out the cost of cavity glass, but you can use cavity glass, of course. So as I mentioned, we partnered with Screen on the nozzle printing. This is a picture of the first Generation 4 glass size printer, which was installed in Santa Barbara. It was the first one made by DNS, and we used it together to develop the technology and the process. It has very high throughput. It's got 15 nozzles. The head moves at 2 to 5 meters per second. It has great printing uniformity, and it very sparingly uses materials. So to talk a little bit more about the printer, the stage moves in the Y direction while the head moves back and forth in the X direction, printing in both directions. So you don't waste time having to traverse back to the beginning to print. You can print in both directions. The velocity of the head is constant in the printing area, but otherwise it's accelerating or decelerating to either stop or start at the end of the plate. So now I want to take a little bit of time and talk about the importance of luminance and thickness uniformity. Both of those are very important, not just for device performance, but also for display appearance. So we worry about intra-pixel uniformity, we worry about short-range uniformity, and we worry about long-range uniformity. This schematic just shows a cartoon of good and bad intra-pixel uniformity. So here the layers are nice and flat, here they're domed and kind of asymmetrical to one side. And then these are some EL images of a pixel showing corresponding good and bad uniformity. So we developed an automated system to measure 16 locations on our standard 6-inch by 6-inch plate. So we use the stylus profilometer, we measure 16 locations, and then we wrote custom software to extract the printed layer thickness throughout the pixels. We use an empty well. This is a monitor device, so it's not one that we actually finish into an OLED for measuring thickness. We leave some wells empty, and then we measure the difference between the empty well and the printed well to get the printed layer thickness. In this case, it's about 450 angstroms. These high areas here are the banks on the substrate. So we can achieve greater than 95% thickness aperture, and we can get about 2 nanometers thickness variation across the whole plate, which gives you a long-range uniformity of greater than 90%, which is very good and very adequate for commercial uses. So long-range uniformity is not the hard thing to do. The harder thing to do is intra-pixel uniformity and short-range uniformity. Short-range meaning pixel to pixel or short order. These are luminance measurements. So we measured thickness in the last slide. Now we're looking at luminance uniformity. This is our standard 6x6 plate that we make many of every day in our semi-automated line in Santa Barbara. So these are 16 printed devices, and we routinely then will take high optical microscope images of areas in these pixels and then measure the horizontal aperture and the vertical aperture, and those are listed here for standard parts. So you can see that we can get very nice flat films using our printing methods. So I think it's very commonly understood that a challenge for all solution printing methods is difference in flow or volume out of different nozzles. And an example of that is shown here. So for example, if we intentionally vary the thickness of the EML coming out of one of the nozzles from the others, you can see a periodic dimmer line as you go across. And that's what we call a stitch, or people call it a swath mark also. And then what you can see is if you can reduce that thickness variation below 3%, then you don't see anything. So this is just an example. This is a 4.3-inch diagonal passive matrix display with 5 nozzle printing, just to show you an example of stitch and getting rid of it. But the human eye isn't really good enough to see everything. So we've had to find a better metric to look at short-range uniformity or stitch. There isn't an automated method, and there isn't a widely accepted method in the industry. However, we have found that there was a paper published by Samsung SDI, as it was then, SDC now, where they compared their evaporated AMOLEDs to commercial LCDs using this methodology. So we adapted this for looking at our printed displays. So what you do is you divide, this is used on an active matrix display now. So we divide the whole display into 8x8 arrays. We measure the luminance of each pixel in that 8x8. And then we look at the ratio of the max to min luminance for each of the segments. And then the overall number that we get is the average of all of those 8x8 arrays. So commercial AMLCD, as it was measured earlier this year by us, is 93%. And then our printed red, green, and blue AMOLED subpixels, you can see, are at least as good and actually always a little better than the commercial AMLCD. So we bought the most expensive, best quality AMLCD we could find. So this is the methodology that we use, and it's much better than the human eye because it depends on viewing angle, depends on the age of the test engineer, how much they see. So it's better to have something that spits you out a number. So now I'd like to turn and talk about the scale-up path to large area manufacturing. So I think everybody agrees that OLED's very appealing for large format displays, the very beautiful images, narrow, thin displays, very good format, very pleasing appearance. However, today, even small format OLED is cost disadvantaged versus LCD. So we wanted to try and address that, obviously. So there's really 3 key barriers to overcome to make OLED television successful in our belief. The first one, which I think we've met, is that the material performance must be good enough. And then if you look at the current methods by which OLEDs are made, we have to reduce the material deposition waste because we're throwing money away there. And then the OLED material application equipment needs to scale to the same size and productivity that LCD can do. Otherwise, it's going to be impossible to compete. So DuPont has licensed its process technology to a large Asian display maker who's currently a leading manufacturer of OLEDs. Their objective is to reproduce and scale up the process in order to mass produce OLED televisions. The timeline for that is still being finalized. I say that to forestall the obvious question of when we will buy one. But this work is driving the analysis and design and testing of systems required to scale up to larger areas, and even up to generation 8 we're looking at. So the importance of scale for LCD is that LCD cost improvements have been driven by a rapid increase in scale. For every generation glass size increase, the equipment cost goes up by 30%, but the productivity goes up by 50 to 100%, so you can see why they go to larger and larger glass size. OLEDs had a tough time following that path because of the issues with scaling up evaporation. So that's what we want to address with solution. We have been working on scaling up the individual steps of our process and doing that feasibility work. So I wanted to share a little bit of that with you. The HIL and primer layers, as I mentioned, are slot die coated. This is a common process for photoresist up to generation 8, but OLED films are a lot thinner. 20 to 200 nanometers thick. So that presents challenges. We've got to coat at very high speed and very high gap to get, for example, 90 seconds at Gen 8, while we still need really good coating uniformity at a thick layer. So we've had to work on the materials and the process to get those flat films. These are data from a 3.5G test coating that we did very recently, which shows less than 2% total range of variation across the glass. And this is at a 200 nanometer film thickness. So you have to coat it flat, but then after you coat it flat, it has to dry flat within the pixels. This shows you that by playing with the formulation and the process, we can take a film profile, we can achieve a dry film profile which looks like this, all the way through to the other worst case, which is this one. The wet film, of course, is much higher than the topography of the pixel or the well, and the dry film is much lower. So it means that you really have to control your drying and your film formulation and your materials in order to get this desired flat profile. This chart now shows typical display sizes and formats that are here commercially are viewed as coming soon. And you can see resolution on this axis and diagonal in inches on this axis. You can see that there's a natural separation where the higher resolution displays are smaller diagonals, and then as you get out to the TV size, 55-inch TV, then the resolution becomes lower. And these are 4K, 2K is the higher pixel count, and then HD is the lower one. So there's sort of a natural zone of practical resolution versus diagonal that you see when you plot it this way. And what you also is that larger display sizes are typically produced on larger generation glass, mother glass, to optimize productivity. So the larger TVs will be produced on Gen 8 glass, it's believed. So our current nozzle printing is well developed for resolutions up to about 200 ppi. We haven't gone as high as 250 or 300 ppi with nozzle printing. And then the other interesting thing to note is that the print scans are relatively constant even as the substrate grows, and that's because the resolution is going down. So the nozzle printer has to print only approximately the same number of lines for this display as it does for this display because of the resolution difference. So when we think about scaling up nozzle printing to Gen 8 or large generation glass sizes, this example is done for Gen 8. Nozzle printing gives you excellent uniformity because you only have to control two parameters, the flow rate and the head speed. But since the nozzle flow is continuous, the printer parameters such as number of nozzles per head and number of heads per system does impact material efficiency. So material efficiency plotted here is the fraction of all the materials consumed that are deposited on the substrate. So whatever isn't, this is the maximum that can be gotten because some will be jetted while the plates are being changed, for example. So when the material efficiency is 100%, all the material consumed is deposited on the substrate, not thrown away. So for this example, if you look at the number of nozzles per head going in this direction and the number of heads per printer going in this direction, you can see that there is a sweet spot where you've got like 5 to 7 heads per system with about 30 to 40 nozzles, where you've got high total material efficiency. That's including printing and transfer of plates where you're printing into the waste. So that's at about 70%. Now, if you think about material consumption for a printed layer, here, this is the material consumption axis, and the reference here would be 1.0. 1 means where the mass of the material that's needed to just cover the entire substrate area with a layer at the correct thickness is 1. So you've covered 100% of the substrate with exactly the right thickness. Of course, we don't need to print 100% of the substrate because we only need to print in the active area. For example, evaporation, depending on whether it's a point source or a linear source, this number will be somewhere between 3 and 10 because they're evaporating on the entire substrate, but also on the walls and in the evaporator. So there's a lot of waste there. So if you plot, again, the same nozzles per head, but going in this direction this time, and heads per system, and you look at that same area of 5 to 7 heads and 30 to 40 nozzles, your consumption number is about 0.4, and actually can range from 0.4 to up to 0.7. So this is again a model for a Gen 8 substrate, a 55-inch HD TV, RGB printed on one printer, and then with a 90-second tact. So you can see that the material consumption is very low, which is going to give us good cost savings. The other thing, of course, you've got to factor in is capital costs. Capital cost will go up as the number of nozzles and heads goes up. So you have to combine the two. So this is the capital cost as the heads and nozzles changes. And what you find is if you combine the two, you'll find that there's a sweet spot for optimizing or balancing capital cost and material consumption. And that's at about 76% material efficiency with material consumption of 0.4 versus if you factor in capital costs for evaporation, we believe that number is about 2.0. So if you look at depreciation, fixed costs, and material costs, you can actually roll up what you think the cost of a manufactured OLED display will be and compare that to LCD. LCD is it's a relative scale, so this is LCD cost is 1.0 here in this graph. And what you see is that nozzle printing OLED can be about 30% below LCD because of the material efficiency and the scale of the manufacturing that can be achieved. Projected full-scale evaporated OLED is higher than LCD, and then evaporated sixth cut OLED is even higher again because you've got to have extra capital cost because you're cutting down the substrates. You need more evaporators to keep the tact time. So then this just shows the progress of solution processing at DDI over the last number of years. This was the first demonstration of full-color printed AMOLED panels with small molecules back in '06 at SID. At the time it looked gorgeous, but not now. So if I go ahead, this is just through the years. What we showed in 2010 at SID, and then in 2011, this is a 5.8-inch, 83 ppi, 1.1 millimeters thick. So in summary, hopefully I've shown you that solution processing is a key to large area OLED displays, and that our materials and processes are getting ready for large scale. I'd like to thank all the scientists and engineers at DuPont Displays in Santa Barbara and in Wilmington, and the scientists in Central Research also in Wilmington. And thank you very much for your attention.